Okay folks, so we're going to talk about shear diagrams today, how we develop them. So what I'm going to do first is solve for the reactions on this beam. So I'm going to call this the right and the left reaction. So I'm going to sum moments about here, sum moments about here, and then to check myself, sum forces in the vertical direction. I'm going to go, excuse me, I'm going to go ahead and do that off camera since the focus of this is on shear diagrams, and hopefully you're getting comfortable with calculating reactions. But at the very least I'll show you the calcs on how I got there so you can follow that if you need to. Okay, so I solved for the reactions here. I first sum moments about this side, so my moment arm is all from here, so I have 4 feet, then 7 plus 4 feet, and then 7 plus 4 plus 6 feet, and then I have a 22-foot span. And then here, so on this one I wrote everything on the left, set it equal to 0. On this one I set all of the moments going in the clockwise direction on one side and the moment going counterclockwise on the other side of the equation, or the equal sign, which for me is easier to keep track of. And at the end I summed the forces, so I took the input loads, added them together, subtracted out the reactions, and they were 0, which is exactly what I wanted. Okay, so from here what I want to do is find the shear diagram. To do this I'm going to start by calculating the load, or just drawing the load diagram, which will then make the shear diagram really simple for me. So to begin, I'm just going to extend down my lines here just to make it a little cleaner. So I'm going to call this my load diagram. I'll draw it a little dark. So on the left side I have L of 28.4 kips. I have a load of 15 kips, 30 kips, 10 kips, and then on my right reaction is 26.6 kips. Okay, the next thing I'll do is, and I think I'll do this in pencil, so I'll just extend these guys. So now that I have my load diagram, I want to draw my shear diagram. Okay, so as I go from left to right, anytime my pen crosses a load or reaction, or a distributed load, or any load, I need to incorporate that into my shear diagram. So as I come from here to here, I hit this 28.4 kip load, and that's upward. So I draw this, and I'm just going to write 28.4 kips right there. Now this load is constant, or this shear is constant, because there's no load happening in this area. So my shear diagram just stays the same. Okay, now when I hit the 15 kip load, that's downward, so that's going to bring me down to here. And the magnitude right here is going to be the difference of 28.4 and 15. So I'm going to subtract 15 from 28.4. I get 13.4 kips. And then as I come out of the other side of that load, there's nothing, so I'm horizontal in my shear diagram. Now when I get to 30 kips, again I go down, and I can cross the horizontal axis. In fact, I have to. So now my load here is 13.4 minus 30 kips, so I have 13.4 already in there. Subtract 30 again. This point here then is minus 16.6 kips. Continuing on, I don't have anything between these points, so my shear diagram is horizontal. I hit another 10 kips, which is pointing down. I just go down. It's either up or down with point loads. So I'm going to add 10 kips to the minus 16.6, so I have minus 26.6 kips. And then I continue across, and my reaction is positive 26.6, which is fantastic because that means I'm back to 0 at the end. And that's how I know my shear diagram is correct, as if it closes. Say I did this and I came here and I was minus 40, then I would be down lower and come up to about here. Because I'm not closing, that would tell me there's something wrong in my solution. And usually it's in the calculation of the reactions, but sometimes it can be in the way that I'm accounting for these loads. Okay, so with that said, let's pause for a sec. Okay, so I've decided I'm going to go ahead and do the moment diagram for this, because I think we're here. It's just a breath away from us. So when I do this, I like to lay this out as load, shear, moment. Now that I'm doing moment, I need to add the lengths here. Okay, so the moment diagram, the magnitudes at different points will be the area of the shear diagram. And that starts to make some conceptual sense. When you calculate the area here, you have units of kips and feet, which are also our units for moment. So what I'll do to find, well, let me just first draw the shear diagram. And so what happens is this area gives us a magnitude here. This area adds to that. This area takes away from it. And this area finishes taking away to 0. So our moment diagram at each end is going to be 0 because my loads, or my reactions, or my supports rather, are pins. So this is a pin that can support up and down and horizontally. This is a pin that supports only vertically. Okay, so reviewing, my moment is 0 here, 0 here. There's some increase in moment because the shear is positive. So that actually gives me a line that looks like this. And then this gives me additional moment because its magnitude is less, the slope will be less. This is taking me down because it's negative shear, so it reduces the moment. And then this should bring me back to 0. So now I just need to find these points. And the way I'm going to do that is by calculating the area of the shear diagram to that point. I could do it anywhere that I wanted. So if I said, I really want to know the moment here for some reason, I could come in, take this area, times, so this area, which would be the length to this point, times the height, which is the magnitude of 28.4 kips, and that would give me the shear here. Now in this case, I really don't care. I'm going to find these 3 points. What I really want to know most of the time, at least in timber design, is I want to know the magnitude of the maximum. Now in concrete design, I do care about this area of the curve because it allows me to reduce my reinforcing. But for this animal, let's just stick with the maximum and these points. Okay, so I'm just going to call this point A, B, and C. So the moment at A is 28 4 kips times 5 feet. So I'm literally finding the area of this thing, but I'm using kips and feet as my unit, so it's kind of a weird way to calculate area. So that's 142 kips. Okay, now to get moment at B, I need to add this value to the increase from that shear. So moment at B is going to be 142 kips plus 13.4 times 6 feet. So 13.4 kips times 6 feet. Gives me 222.4 kips. So I'm going to just write these up here. And I set those units wrong. It's kip feet. Okay, then moment at C. Now because I'm coming down, because my shear is negative, I'm going to subtract from here the effect of that shear on the moment. So 222.4 kip feet minus 16.6 kips times a length of 7 feet. When I do that, I've got 16.6 times 7, subtract that, I've got 106 kip feet. Okay, now let's find, so that's the moment at C. Let's find the moment here. I know it's 0, but let's confirm that it is 0. So moment at the right is going to be 106.2 minus that area, which is 26.6 times a length of 4 feet. And I'm being a little loose on my units because now I'm rolling, I'm doing a lot of calcs. I know that I'm using the right units and I don't need to be as concerned. And I get minus 0.2, which is close enough to 0 to say that's okay, and it's really a matter of rounding error throughout here that gives me that little bit of error here. Had I carried this out to a couple decimal points, that would be pretty even smaller. Alright, so moment diagram, or shear and moment diagram, we start with loads, go to shear, and go to moment. And this is the shape for point loads. My shear diagram will be rectangular, and my shear diagram, or moment diagram rather, will be triangular. Okay, good luck with it.